Good morning, all, and welcome to the Johns Hopkins Institute for Assured Autonomy and Berman Institute of Bioethics seminar series. I am delighted to welcome Dr. David Danks. He is professor of data science and philosophy and affiliate faculty in computer science and engineering at the University of California, San Diego. He's also a recipient of the James S. McDonnell Foundation Scholar Award, as well as an Andrew Carnegie Fellowship. He currently serves on multiple advisory boards, including the National AI Advisory Committee, and his research spans philosophy, cognitive science, and machine learning, including the intersections of those fields. Today, he'll be talking to us about tackling the intractable problem of bias. Welcome, David. I look forward to your talk.
Thanks so much, Deborah. It's really an honor to be here, and it's the joys of Zoom and other kinds of video conferencing systems that I'm able to be here in San Diego and talking to you all in Baltimore. I suppose I should first say, since Deborah mentioned NIAC, the National AI Advisory Committee, of course, obligatory comment that I do not speak on behalf of NIAC. I'm here speaking solely on my own opinions and views. And with that, I'd like to go ahead and start in. So as Deborah said, what I'd really like to do today is talk about this problem that in some senses, I suspect, not one I need to say very much about to this group, which is the challenge of bias, the challenge of algorithmic bias. And in particular, what motivates the work that I want to talk about today is the idea that we need to start recognizing just how intractable this problem seems to be. We need to start with a recognition that bias does not seem to be something that we just need to find the right fix and away we go. And here I would actually draw a contrast with another area in AI and data science where I think we have made enormous progress, still a lot of questions to be answered, but the area of explainability and explanations of what an AI system is doing. Now, obviously, we have a lot of challenges that remain when we think about explainable AI, to use that term, but we really have made progress. I mean, I think if I just think back to 5 or 6 years ago, the state of the art, we really had no idea what was going on in a lot of systems. And now we have many techniques that do seem to provide the kind of information that is cognitively relevant for us in order to make sense of, understand, and more appropriately use the AI systems that we have in front of us. In contrast, it seems that bias, it feels like we haven't quite made that progress. And I think there's a reason for that. And hopefully I can convince you of my diagnosis and of a path forward that I think can enable us to make progress because it is perhaps a new way to think about the problem of algorithmic bias that is not subject to, or that rather integrates the best of what we've been doing so far. So, okay, so with that, let me dive in. I think one of the things I always think is important when talking about bias to note at the very beginning is to sort of remind people that there's a reason we want to use algorithms. I mean, folks at the IAA probably are thinking, well, of course we want to use algorithms, but especially that there's reasons to think that we want to use algorithms exactly because it seems like they should be less biased than us humans. We know that we humans are subject to an enormous number of cognitive, moral, emotional biases. And it certainly seems to be the case that algorithms ought to be better than us in that regard. Algorithms are repeatable. They basically do the same thing every single time, assuming that you don't have too much stochasticity in the actual algorithm itself. They are objective, and to the philosophers in the audience, yes, I understand all the complications in using that word, but nonetheless, algorithms aren't necessarily going to be swayed by the more ephemeral subjective perceptions that we humans might have. Now, we might think the subjective perceptions are good, but in many cases of ethical bias, we think that those subjective perceptions are exactly the problem. I would also note, in connection with what I was saying about explainability, algorithms are auditable. You can look to see why, in some sense, they did what they did. And here, I think there's a quite stark contrast with human cognition and human decision makers. We are actually quite bad at recognizing our own motives and reasons for action and decision. I mean, we're not terrible at it. We're not at chance levels of recognizing our own motives and reasons. Nonetheless, we are a long way from the kinds of things that we might expect to see in an algorithm, the kinds of abilities that we have with algorithms to understand what's going on internally to them. And so, this is a somewhat technical audience at times, so obligatory XKCD, right? One problem with this whole idea of the intuitive appeal of algorithms is it turns out the world is a messy, complicated place. The other is, of course, that algorithms are optimized for particular purposes and to achieve particular ends. And those may or may not be the things that we actually cared about. Okay, so there is a precision that comes from using objective functions and loss functions when we optimize, but that also comes with risks of, are we getting the values right? Are we thinking about this appropriately? And so in some sense, it's unsurprising that bias is this issue that keeps resurfacing. On the one hand, algorithms do not necessarily have all of the features that we think of as making them intuitively appealing. On the other hand, we have to make them precise in ways that can actually distort and lead us down problematic pathways that can lead to, again, this is sort of an obligatory slide. I don't think I need to go into much detail, but the rather large number of cases that just keep coming up over and over and over, where the use of algorithms has led to the creation, the perpetuation, the exacerbation of societal, ethical, and statistical biases. Right? So we want to do something about it. What can we do? Well, the first thing I think we need to acknowledge is, and this could be sort of its own talk all on its own, but is the complexity of just talking about bias in the first place. Much as with explanations, there are many functions that explanations serve, and so we have to think carefully about distinguishing them. We also have to think carefully about different kinds of bias. So bias, as I prefer to use the term, is essentially a deviation from a norm or a standard. And we can have statistical norms, moral norms, legal norms, and so on. And so you can have different kinds of biases that can in fact come into conflict with one another and lead to irreconcilable trade-offs. The most obvious case of this is when I have data about a morally biased social system. Okay. Any model I build on those data will either have statistical biases, because I correct it to be morally appropriate, but that means I am not mirroring the statistics, the historical statistics in my training data. Or my model will have to be morally biased, because if I correctly mirror the statistics in my training data, I will thereby be replicating the moral biases that are in the social system. Okay, so the very idea of an unbiased system is one that you should just set aside. There is I do not know of a case where we can talk about an unbiased algorithm. Every algorithm is biased. In fact, some biases are good. When we talk in statistics about the bias variance trade-off, we're using statistical biases to reduce the variance of our of the estimation process for our model. That's a good thing, right? So we have to be really thoughtful here that bias is not an intrinsically bad thing. The problem with biases is when they lead to moral, social, psychological, material harms to certain communities, certain groups, certain individuals. Okay? It's not an intrinsically bad thing, though, to deviate from a standard. It might actually be the right thing to do in order to achieve the ends that matter to us. Now, related to the complexity of algorithmic bias is not just the different kinds of bias derived from the different norms or standards against which we have a deviation, but also the many different sources that we can have. This is, I'm teaching a data ethics class right now. We spend 2 entire classes talking about all of the different reasons why we can end up with various kinds of biases, ranging from the real world being biased, right? This is the kind of standard thing that people point to and say data on hiring algorithms, up to biases in the ways that we deploy our algorithms. So I can have a diagnostic AI system for healthcare purposes that works beautifully in an unbiased way in the UC San Diego healthcare system. That doesn't mean that I want to deploy it, that it will be unbiased and wonderful if I deploy it in the Central Valley of California, which has a very different population, very different access to healthcare resources. Or of course, if folks at Hopkins Medical Center were to build a great diagnostic AI system and then deploy it in Western Maryland, essentially West Virginia, Southwestern Pennsylvania, it may not work as well. You're dealing with a very different community, right? So biases can show up for all kinds of reasons. And one might think, oh, okay, now I see where Danks is going with this. Bias is intractable because it's not one thing. It's this plethora, this multiplicity of things. And that's why it's intractable. That's actually not where I'm going with it, with this talk. Because I think that although there is complexity here, it is in a certain sense tractable. It's combinatorially tricky, right? We can ask questions like, what are the social biases that manifest through training data? Or we can ask, what are the legal biases that manifest through the interpretation of a model output by an end user, right? Yeah, there's a kind of combinatoric complexity that's frustrating and leads to very long papers because you have to have lots and lots of subsections. But that's not actually something that's intractable, I think, in any deep or interesting way. It's just hard and takes more time, okay? The intractability seems to be coming from a different place. So what I want to do now is to talk about what I think are sort of the standard approaches from a technical perspective and from a policy perspective to try to do something about bias and talk about where I think the shortcomings are of each. Okay. Now, I want to emphasize right from the outset that when I'm talking about these standard approaches, I am deliberately painting with a very broad brush. Okay, so the next few slides, if you have the reaction of, yes, but what about this particular paper where they did something different? I would simply encourage you to A, throw that in Q&A and we can talk about it at the end of the talk, but B, reflect on whether that might be the exception that proves the rule. Okay, I'm not saying that nobody has thought about some of these issues. I'm saying that here are the standard approaches and why I think they're falling short at the moment. So what's the standard technical approach? So the standard technical approach is, start with basic machine learning, AI, data science, whatever your preferred terminology is for this pipeline. You give me data over certain variables and I learn a predictive model that if you give me a new individual with partial specification of their value for those variables, boom, I give you an output, right? So you give me a bunch of training data on images of people's skin, along with labels of whether it's cancerous or not, whether it's a melanoma, and I learn a model that you give me a new picture and it will make a prediction of whether you have melanoma or not. Or you give me data about the functioning of college admissions, sort of who gets admitted, and I can give you a predictive model that says, here are the people most likely to be predicted in next year's undergraduate class, right? So maybe we use that to get rid of a human who is making that decision. Maybe we use it to augment the human decision maker. There's lots of different uses, but that's the basic idea, right? You give me data, I learn a predictive model. And then I'm going to measure fairness by some measure, mu, that would be applied on the target population, which may or may not be the training population, right? It may be that my training data come from an unrepresentative sample, okay? And so I'm going to need to figure out how well my model is going to do on some other population. Now, I don't want to bore you by showing 1,000 different equations, most of which would flash up far too quickly for you to process. So instead, I'll flash up some words that are probably too much for people to process at real time at 11:15 on a Friday morning. The point is simply that there's really been an enormous number of these measures that have been proposed. Each of the measures comes accompanied by almost always some essentially philosophical justification, right? If we think of fairness as treating all the same, well, then we've got 2,500 years of philosophical work on what it means to treat people the same, and a recognition that that's a somewhat vague term that can manifest in many different ways, be operationalized in many different ways, and that's what these different measures represent. Okay, the different measures, they're different equations, but what they really are is they are different operationalizations of philosophical intuitions about what it is to treat people the same in some sense. And then, people have shown that there's various impossibility theorems in the sense that you can't get to zero on all of these measures unless the world is incredibly cooperative. For essentially any real world case, you're not going to be able to have something that minimizes fairness on every measure simultaneously. Okay, so in other words, speaking philosophically, our philosophical intuitions are in tension with one another. That what the technical approach has revealed is that, in fact, the goal that many philosophers have had, what is the meaning of fairness, turns out to be almost certainly an unsatisfiable one. We just can't actually have systems or methods or procedures that are going to be fair according to every one of these intuitions. So we're going to have to pick and choose. Now, that part is interesting. The mathematics of it, yes, I enjoy that part of it, but I think it's also important to recognize some features that are, in essence, measure agnostic. Okay, so these are things that are true of everything from the previous slide. In all of them, bias is measured by deviations in the observable statistics. Almost always there is a caveat. There are a few people starting to do work on so-called causal or counterfactual measures of bias. That's been in the last 2 or 3 years. There are issues with those as well. They're better than what was on the previous slide, but they still are driven in many ways by the observable statistics. Okay, I'll come back to that if people want. But the point is, bias becomes discrepancies or differences in observable statistics on the standard technical approach. It is viewed as essentially that there's a one-to-one mapping. If you have deviations or differences between various measures that apply to the observable statistics, then that is just what it is to be biased in some way. And so if that's the way we think about it, there is an ideal state. Okay, if we think in terms of what is the optimal, what is the target that we should have for our policies, okay, not just for the technical machinery, but our policy goal should, on the standard technical approach, be get mu to zero, right? That's the goal of everything we do. When we attempt to mitigate algorithmic bias on the technical approach, what we're doing is whatever our preferred mu is, we're trying to find ways to drive that to zero. Okay, that is the idealized goal. And so therefore, if I think as a policymaker, my goal is to try to reduce mu. So if mu is at 0.3 and Deborah comes to me and says, I've got this idea for a policy change that will, we predict, lead to a mu of 0.2 instead of 0.3, that is, ceteris paribus, all else being equal, that's going to be morally defensible. Right? Because what I've done is I've made a fairer, by the measure that I have adopted, a fairer, less biased system, world, essentially, as manifested in the statistics. Now, I think there are sort of, from my perspective, 3 very big concerns about the technical approach, the standard technical approach. The first is that it focuses on bias in model output rather than bias in the overall outcome. So when we think especially about legal, psychological, social, moral biases, what matters is frequently not that the model outputs some particular number, but what happens overall with the system. Do people disproportionately harmed? And where this shows up with a challenge to the standard technical approach is in 2 ways. First, the standard approach focuses only on the model rather than the model, human decision maker, broader socio-technical system pairing Okay, so the first thing is already that we've got a problem because we need to think more holistically about the system, not just about the single model. The other place it shows up is that different errors might have radically different impacts on different communities. This is just the simple, you can start with the simple observation that false positive, false negatives might have different impacts on different people. It's not the same to tell me that I have a disease when I really don't, as it is to miss a disease that I actually do have. In the first case, I undergo more tests, which might be problematic, but in the long run might not be that much of a marginal cost. In the latter case, it might mean that it goes untreated for a long time, in fact, perhaps reaching the point that it is now untreatable. Okay? And so we're used to this idea that false positives, false negatives don't have the same impact. But we need to recognize that's also true when we think about errors in a community-specific way. Okay, so if we think about bias as we want to treat all the same, or fairness as we treat all the same, then we need to think about not just whether the model is outputting the same things, but whether people have the same impacts on them. Okay. A second issue is the sort of already been hinted at observation that moral biases are not the same as statistical deviations. I can give you, basically, you pick the measure. We can play a game. You pick the measure. I can get, and you give me statistics that are as optimal as you want according to that measure. And I can tell you a story, give you a proof of concept where there is significant moral and often legal bias, despite the statistical measure being as small as you want it to be. Okay. There are connections between moral biases and statistical deviations. They are not uncorrelated with each other, but they are also not identical with one another. And so it is neither necessary nor sufficient to, as the second bullet point on this slide says, drive mu to zero. That is neither necessary nor sufficient for the removal of moral, legal, social, psychological biases. In fact, there are times we should try to increase the statistical bias in order to reduce the moral bias. Okay. So that's, in some ways, I think arguably the biggest problem is that the technical approach essentially tries to reduce all those other kinds of biases to measures that are fundamentally statistical in nature. And that reduction doesn't work. It's always going to fall short. And so we're going to have cases that are where we have been very successful statistically and very unsuccessful morally. There also are challenges with the standard approach about sort of local versus global fairness. So we can also show that in a lot of different conditions, you can be perfectly unbiased on every individual decision, but your collection of decisions is actually globally biased. Okay, so again, we can play the game of you pick the measure, you pick the scenario, and as long as you give me a little bit of freedom in terms of designing the statistical, basically the joint distribution, give me a little bit of freedom in designing the joint distribution, and I can make it so that you will be biased globally, even when you're unbiased locally. Right? So the way to think about this is every decision is the right one, and yet the collection of decisions is wrong. It is not the collection that you would do if you were just deciding the collective all at once. Okay, so that's another problem, is that the technical approach inevitably is going to force us to decide between local and global because everything comes back to what is my one measure. Okay, so I mean, you can define a measure over the global fairness. You may not be able to realize it because it may be that you can't make decisions for a collective. You might have to make them individually. So you can define a mu, but then that is going to be a problematic one from the local. Right? So the kind of one measure to rule them all idea that often lurks behind the standard technical approach is the problem here. Now, one thing that I think is sort of the theme of all of these is that bias and fairness are fundamentally not definable in purely technical terms. So the mistake, in some sense, the original sin of the standard technical approach was the idea that we could use purely technical means to tackle the problem of bias and unfairness. In some sense, we never should have expected this to work. It is an important first step. These are important tools that are being made available. But the idea that this would be sufficient for tackling the problem of bias, in some sense, we never should have expected that. Because if we learned anything about bias and fairness from 2,500 years of philosophy, it would be that these are not purely technical matters. And in particular, the context and details matter. It is important to think about what is the domain we are operating in. Who are these people? All of this context specificity really matters. And that's exactly what statistical technical approaches try to abstract away from. Part of the power of statistics is precisely, and AI and machine learning is precisely that they abstract away from some of the messy substantive details of a particular context or problem. And the worry is, well, we're just going to have to address that in some way. Okay, well, how do we address messy complexity? Well, here's a good way to do it. It's policy. That's something we're kind of used to. There are two, I think, standard approaches people are taking right now to policies around bias and fairness. The policy work in this space has lagged behind the technical. It's running, I would say, sort of 3 to 5 years behind where we are on the technical side. So this is still an area that's very much in flux. But we're, I think, quickly seeing the emergence of two different approaches that people are taking to policy around bias and fairness. So the first is kind of the simplest one you might think of, which is, well, let's just turn the technical approach into policy rules. Okay, let's just do a straightforward translation. There's all this technical machinery translated into law. So the most obvious is last year, Law 144 in New York City, which is focused on automated employment decision tools. It's a very narrow scope, but it is arguably one of, if not the first serious regulations of algorithmic decision-making tools in the United States, this one at the municipal level. There have been lots of task forces. There have been various ordinances, such as in Santa Cruz around predictive policing, but those have not necessarily tried to regulate the algorithms themselves. And what's notable about 144 is that it does not ban the use of these systems, but rather attempts to regulate them. And the big key here is this term bias audit. Now, I haven't included the text, but essentially a bias audit is using one of the technical approaches to try to understand if there's a non-zero number for some measure. Okay, that's essentially what the bias audit is. It is take that technical machinery and use it. Okay, and this is, I again didn't quote the rest of 144, but this is the dominant piece of the legislation. The dominant element of this particular law is that if you're going to use an automated employment decision tool, you have to check it using one of the technical measures for bias. There are other pieces like you have to disclose and give people recourse and these kinds of things, but this is the only part that's relevant to bias and fairness. Okay, but this is of course going to inherit all the problems from the previous slide because this idea of translating the complexities and domain specificity of bias into a particular measure inevitably is going to fall short. We are again going to have companies that will be able to truthfully and correctly say, we passed a bias audit, while they nonetheless are using an automated employment decision tool that is morally biased. Okay. So this approach just inherits all the problems of the others, so I'm not going to spend much time on it, but it is one that is starting to show up. The other approach is, I think, a more interesting one, which is rather than trying to focus on the measures of the model, it's instead to focus on the practices and processes that lead up to the model and are involved in its deployment. So one nice example of this is the recent algorithmic bias playbook that came out of the folks at the University of Chicago. They have this whole, copied it here in probably too small print, but the playbook is free to get. I encourage you to look at it if you have not yet. But the algorithmic bias playbook, they give a 4-step process to trying to eliminate bias and fairness. And crucially, only one of those half steps, step 2B, is the only one that involves elements of the technical approach. Okay, everything else on the right-hand side there is fundamentally about the socio-technical system. It's about the people. It's about understanding what bias means in the particular context. Okay, so these practices are all the kinds of things that we would need to do to understand what bias really is in this case. It is all of the things that you would have to know in order to really have a thoughtful, well-crafted, substantive theory of bias in, say, this particular domain of healthcare. Okay. A very similar kind of strategy is actually in the recent NIST document on identifying and managing bias. If you look at what they write in terms of recommendations for managing bias, what you see is a lot of different steps spread over multiple pages. That's why I didn't screenshot them here, but a lot of different steps. And again, only one of them actually makes any reference to what happens in the standard technical approach. Okay, so this second policy option is basically to say we recognize that the technical approach is insufficient, that we need to understand the complexity of the situation that we are working in. And so therefore, we will give you a set of practices that enable you as a developer, as a regulator, as management at an organization, that enable you to, in essence, construct the kind of bespoke solution that is needed for the details of this particular case. Okay. Now, the challenge, I think, for this second approach is twofold. The first is that word I just used, bespoke. So first challenge is this doesn't scale terribly well. If I go back to the algorithmic bias playbook, this is a wonderful set of recommendations. It is also requires a kind of specialized skill and knowledge that is not necessarily going to be universal across organizations. It requires a tremendous investment of effort. It is an investment that I think is often warranted, especially for high consequence cases or situations. But nonetheless, it is not necessarily scalable. Okay, so that's one issue. The second is, while this bias playbook is useful, is a good guide, the NIST document it isn't itself a standard. It is towards a standard. And that's the second challenge, I think, with the identified practices is historically with technology, we've struggled to find ways to codify practices to a sufficient degree of specificity that we can audit them, that we can regulate them, that we can govern using them. Okay, it's not to say we can't do it. There are best practices in cybersecurity, for example. IEEE and ISO come out with lots of standards that are practice-centric. It's not impossible, but it's much, much harder and suggests that we are a lot further away from having usable regulatory guidance and mechanisms than we might have hoped. So what I want to do now is pivot here in the last, call it 10 to 15 minutes, to argue that actually the problem is that we need to rethink what we're trying to do. So the technical approach ran into trouble because it assumed the bias was the domain general. That's sort of, we want to have a way of approaching the problem that doesn't actually engage with the messy complexity of the situation. Okay. The policy approach either inherits those problems or doesn't provide the kind of precision that we need, because it talks about very general practices or it talks about them in ways that cannot necessarily be operationalized so that they can scale to new organizations, so that they can be regulated and audited appropriately, so we can have appropriate oversight. So then we're left sort of saying, okay, so what do we do? I mean, look, it seems like what I'm asking for is something that could be context specific and precise. And you might be saying, okay, great, that's like asking for a square circle, right? Almost by definition, as we become more context specific, as we engage with the messy substantive complexity of the world, it's going to be harder and harder to have precision. Right? I mean, we're seeing this in the case of a lot of things around, say, assured autonomy, right? We want our vehicles to drive safely. How do we become precise about that? Well, we can become precise only by having very high-level characterizations that we can specify, but that don't necessarily operationalize universally Or we have, as I put in the parenthetical, a problematic proliferation, right? We get 5 million different special cases, which has its own set of challenges. So what I want to do is I want to actually take what may seem like a completely bizarre digression to suggest that there is, in response to this question, how can we be context specific and precise? We've actually done this in a different field, I want to argue. I think that we actually have made enormous progress towards having a context specific and precise formalizable, regulatable framework, but in a different field, in a different domain. And that different domain is the domain of causation. So I want to have a brief digression about causation, and then I promise I'm going to, as I say here, draw an analogy back to bias, okay? So statistics 101, correlation is not causation, right? What we really mean by that is that statistics are not constitutive of causation. Telling me the statistical profile is neither necessary nor sufficient for determining the causal relationships of some system. And what C causes E means is going to depend a lot on the particular domain and the context. Telling me that the meaning of aspirin alleviates headache is not the same sense of causation. There are important differences between that kind of mechanistic causal relationship and say, my daughter's anger causes me to be sad or something like this. I have a teenager, so I tend to think about those kinds of social phenomena. So the statistical relations are not constitutive. We have to think about the particular domain and context. But it is the case that the statistics are informative about causation. And so, in fact, there's been an enormous amount of work in the last 35 years, developing methods that can extract and learn the causal structures that could produce data that look like this. Okay, so the big advance in causation, you may have heard about this on the AI side. Ooh, causation, it's very hot topic these days. The real advance in causal inference methods is not the algorithmics. It's actually the conceptual move to say we are no longer going to try to understand causation in terms of the statistics. Rather, we're going to use the statistics as evidence for the causal relations. Okay. And so we have to be really thoughtful and careful, and we have to do things like distinguish between population level causation and individual level, right? We want to say things like smoking causes lung cancer at the population level, but my uncle's smoking didn't cause his lung cancer. It was exposure to radiation that caused it, right? These kinds of things. So we need to have levels, right? We need to be able to think about different levels of causality. We need to think about the interactions between those levels, ways of moving between them in principled ways, okay? So these are all things that have kind of been worked out in the causation community over the last 35 years. Obviously, lots and lots of open questions, but it looks a lot more like the explainable AI field, where we've made enormous progress and we understand what we can and cannot do. Okay. And I want to suggest that actually bias looks remarkably similar here, right? That statistics are, as I've argued repeatedly here today, not constitutive of bias. The content of it depends on the domain and context, but the statistics is useful. It's why the law looks for disparate impact in order to infer disparate treatment and animus. Bias is separable. We can coherently say that that the healthcare system is biased against that there's racist practices and structural biases built into the healthcare system that lead to worse health outcomes for communities of color in this country, while also saying, but this person's heart disease is not caused by structural racism, right? So a lot of the things that I was saying about causation, you just swap in the word bias and it feels awfully similar. So this is the intuition, is that there's a useful analogy. So what would it mean to put that analogy to work? Well, if causation is fundamentally an unobserved relation that produces the statistics, right? If that's fundamentally at the heart of what has led to the transformation over the last 35 years in AI and machine learning work on causal discovery, what if we said bias is an unobserved relation that produces statistics? I mean, that feels right to me, that biases are these unobserved relative to our data set and our model, these unobserved processes. and structures and relations between people, organizations, broader societal arrangements that lead to people not being treated the same, either collectively or individually. That should hopefully resonate with you that, yeah, when I think about, racial bias in the healthcare system in the United States, it's not the statistics. It's not that people are necessarily treated in measurably different ways. It's everything, it's all the other stuff that manifests in that differential treatment. So, okay, so if we want to do that, how can we discover or identify the unobserved causes or biases? This is the work that I and others in my research group have been engaged in over the last year to 18 months, is we start with how does this work in causality, in causal discovery? What have we been doing for the last 35 years? You start with a way of representing and talking about causal structures. That gives you ways of essentially predicting, here's empirical data that I would expect to see given that this is how the world actually causally works. Once you have that, you can then make the reverse inference, right? If you give me the data, I can ask what structures could have produced or are likely to have produced data that look like these. Okay, that's fundamentally what all of the causal discovery algorithms in the literature right now do. They essentially start by being able to say, here's how causation shows up in statistics. So if you give me statistics, I can, and that's the computationally hard part, find in an efficient manner the causal structures that could have produced something that looks like this. So the question is, could we do exactly this, but for bias structures? Okay. So instead of trying to do it for causation, let's do it for bias, because bias is related to causality, but it's not identical with, right? It's not exactly the same problem. You can have structures that produce biases that are not usefully understood as causal structures. And of course, you can have plenty of causal relationships that do not themselves produce any problematic biases. So what does that mean more practically? So on practical terms, what that has meant, we've been doing for the last 12, 18 months. I thought about presenting you, messy, ugly technical details. And then I thought on a Friday, nobody wants to see that, but please, I'm always happy to go into those technical details if people want them. But we've essentially been pursuing a 4-part path, and we've made pretty good progress. I'll talk about it as I go through the 4 parts here very quickly on most of these. So the first is basically, how do we represent structures of biases? How do we represent these unobserved relationships that are the moral, ethical, legal, social biases, psychological biases that we want to be able to discover from the statistical evidence that we are provided? We are, I think, 90% of the way there. We basically have a representational language. It's built on top of the language of graphical models, for those for whom that is a relevant term. The thing that makes it particularly difficult is these have heterogeneous semantics on the graphical model, which is to say an edge from X to Y does not necessarily mean the same thing. That edge can mean different things. And so that makes the inferential operators much more complicated to specify. But we basically have the representational language worked out. We then have to have methods to get from structure to data. Those turn out to be actually pretty easy. I thought that was going to be a hard part of the puzzle. That turned out to be one of the easiest parts of the puzzle, so that was nice. We then need to have methods that go the other way, from the data back to the structure. These discovery methods, we now have a preliminary method that is computationally really, really intractable. So it's not one that we can use on real world data sets yet. But nonetheless, it is, we have a sort of proof of concept that this is not an unsolvable computational problem. And then the part that we're working on right now is how we implement this for real world practices, especially looking at cases involving healthcare. That's why I keep using it as an example, but looking at systems, especially that can operate on data about both community and individual level health outcomes. Our particular focus right now is on cardiac disease and suicidality, looking at using this kind of thing to understand the biases both in the world and in our model that, that make these very challenging, ethically very challenging problems for us to try to solve. Okay. So why do I think that this sort of bias discovery is the right path? Well, I think what this does is it actually gives us the representational language, the precise framework that nonetheless is guided by the context specificity information, the context specific information. So we can distinguish between different kinds of contexts. We can bring our rich qualitative knowledge from the social sciences and from the humanistic disciplines. We can bring that to bear on this problem, right? Instead of viewing it as a technical challenge or a human social policy problem. Bias discovery gives us a framework in which we can recognize both of these dimensions simultaneously. For those who might be interested in this, it turns out it raises a whole new set of policy issues that, to my best of my knowledge, nobody's talking very much about right now, which is it makes it very clear that sometimes we will have a trade-off between actually mitigating biases we know are present in the world and finding out what those biases are, and can raise questions about whether our policies should help us epistemically understand the world versus helping us ethically, making people's lives better. And it also very naturally translates to thinking not just about the algorithm, but about the human plus the algorithm. So the representational language straightforwardly incorporates social and institutional structures. And so again, we are able to bring diverse perspectives to bear on this problem, rather than thinking that any one perspective is going to be sufficient. So with that, I'm just going to quickly toss up the conclusions for people to read. I know we're at time, and I want to have time for some questions. But I think, you know, this problem has been intractable, not because it is in theory intractable, but because we've been trying to tackle it with single kinds of approaches. And what we need is really a joint technical policy, or said differently, technical human-centered solution that can be both precise and context-specific. And that I think that bias discovery provides us exactly the language and framework to try to do that. So with that, I'll say thank you very much, and would love to talk about some questions. I saw some pop up in chat, but I apologize. I didn't want to try and read them in real time. So thanks.
Terrific. Thank you so very much. And please imagine a room full of people clapping. That one of the big losses in Zoom land. So we do have, I think, a comment and a question in the chat. And then we also have some questions here on Zoom. And I have a question myself, but why don't I start with one of the comments that you didn't have time to read because you were actually speaking. From Tom Lippincott, it seems like there might be a danger in moving away from the utilitarian treatment of individuals as the grounded empirical unit of value. For example, taking a naive example of using macro F-score across intersectional communities, it creates perhaps even trickier issues, and if and how those communities are reified.
Yeah, that's a great question. Hopefully, as you suspect already said, the question may be addressed shortly. Part of it is addressed by having in the bias discovery framework that we have essentially multiple levels. So we have an explicit representational language for talking about social structures. Now, you're absolutely right that we have the risk of reification here. That by virtue of the particular ways that we define the communities operationally, we risk thereby reifying them in ways that are wrong. I mean, maybe we as researchers think that this is a coherent community, a community of, that Black individuals form a coherent community or group, but in fact, there's important differences within that community with respect to, say, healthcare delivery. That's absolutely a worry. And the pushback that I would give, or the response that I would give, is to say that I think the key is that the framework that we're building does not require any sort of strong reification of the groups, exactly because we view pretty much all the interesting action is happening in unobserved latent space, and it manifests in observed statistics. So we have the conceptual resources to say that although we operationalize a group in a particular way, we do not thereby reify it as an actual real thing. Okay, so we operationalize without reification. Now that's a very philosophical distinction that is, I do worry about in practice. You know, you deploy this system out in the framework in the world, and our people are going to do that. But that would be a longer discussion in philosophy of science. So yeah.
Great, thanks. Kyle Doubleday asks, to what extent does the implementation of a bias reduction policy fall on regulators versus ML and data science practitioners to self-regulate?
Yeah, so you know, as this probably will be unsurprising given the conclusion that I had that what we need is joint technical policy. I think it's got to be a collaboration. I think that regulators are not going to be able, in a lot of contexts, to set enforceable rules with the specificity that's needed to actually have them translate to better action. I also think that machine learning folks, myself included, often lack the domain and context knowledge that you need to really understand the unobserved relations and structures that can lead to biases in the particular problem you're tackling. That's not universal, I want to be clear. There are a lot of people who have incredibly deep knowledge about the fields they work in. But I mean, just to use, I'll pick on myself here. You know, we're working on a project looking at issues having to do with cardiac disease in communities, low-income communities, especially here in San Diego County. And the reality is I have a very limited amount of medical training. I don't live in one of those communities. I do not identify with many of the people in those communities in the sense of having the kinds of identifications that would show up. And so I have to collaborate with people who understand that. And I think the same is true of the policy and regulator folks. I think regulatory individuals often have that deep knowledge and so can be very good partners with the technical folks. So I think it really has to be joint. I don't think self-regulation is going to end well, in part because of the fact that, you know, part of what has made ML and AI so great is that we can wander into spaces that we don't necessarily have the enormously deep knowledge. So, yeah.
Great, thanks. Tony, do you want to unmute?
Sure. Thanks, Deborah. And David, thanks for an excellent talk. I really enjoyed it. My question is that in assured autonomy circles, we often talk about trust monitors and other kinds of guardrails, which is kind of funny because basically we're saying, let's use AI by getting away from AI. But, you know, an example might be some kind of distance monitor in an autonomous vehicle just to make sure that the AI isn't telling the vehicle to drive into a wall. Is there some kind of sensible analogous method in terms of trust or guardrails for bias that sit outside of the system itself?
Yeah, so I actually think a lot of the work that's happened in the technical approach could be translated into those kinds of guardrails if we put them, you know, sufficiently far away from the model itself. So I actually think a lot of the problem with the statistical measures is not when they are far away from zero telling us that something's wrong here. It's the idea that getting close to zero means something is right here. So in fact, a lot of those measures are remarkably good at signaling something's gone wrong here. Maybe we need to take this model offline while we try to figure out what it is. So I actually think that we already have a lot of those modules, a lot of those methods on the shelf ready to go, but it requires a reconceptualization of what they're about. If we have to reframe the statistical measures of bias and fairness, not as measures of things that we should optimize, but rather as warning signals that should trigger further investigation. So I actually think we have exactly what you're asking for ready to go, but it would be using them in a radically different way than people are using them right now.
Thank you.
So Alex Stevens asks, could you provide an example for your bias discovery process to help him understand the framework?
Sure. This would be, I could also do this as a, an hour-long technical talk going through the details. So I don't have the time for that, but I'll just quickly say, so take the case of cardiac disease here in San Diego County. So what we're looking at is, first step is using the representational language, which is essentially thinking about what are the relevant factors, essentially random variables, but not exactly, that are present within the community, and understanding the ways they might be related to one another. And so we get a sort of space of possible models that could be the structures that could lead to bias, or could, in fact, be a completely unbiased way that the system works at both the collective and individual level. We then have methods that enable us to basically do the forward inference on that and say, for each of those models, I can tell you what kinds of statistics we would see. And so then what we do in reality is, once we specified the model space, you give me actual data from Family Health Clinics of San Diego and from UCSD Health, and I can now do the kind of reverse inference where I say, all right, what are the models that could have produced data that look like these? We then augment those models, supplement them with the specialized domain expertise. So domain expertise is coming at the front end and the back end, and front end in the model space, back end in model interpretation, to be able to say, we have reason to believe that in San Diego, in the communities we are looking at here, that in fact, the problem is not from the healthcare provider bias. It is not that we actually are not finding evidence that the healthcare providers, the doctors themselves, are biased in important ways. Rather, what we are finding is that the evidence is about allocation of healthcare resources across the county, that the problem is people not having access to it. But it could have been that it turned out that actually, no, we've got really racist doctors in these communities. I mean, that is something that we entertained as a possibility. So that's really what, that's an example of what we're able to do, that we see these divergences and we infer what seems to be going on in light of those data. Now, I want to emphasize, we could have done exactly the same thing if there had not been these divergences in the first place. The fact that there are differences in cardiac disease rates and treatments between UC San Diego Health and FHCSD, that's what prompted the investigation. But actually, some of our models that we entertained as possible would have predicted no difference, even despite there being bias. Okay, so I want to be clear, it isn't that we just sort of said, let's do the deep investigation to figure out why we see this statistical difference. The statistical difference happened to prompt it. But the key to the bias framework is that it's really about specifying ways the world could be at multiple levels involving multiple kinds of relations, and then making inferences from data back into that space to get hypotheses of what's really going on so that we can design targeted mitigation and response measures.
Great. Thank you so very much. We're at the top of the hour. So again, imagine raucous applause. And I hope everybody has a lovely weekend.
Thanks so much for having me.